It's very easy to load it in the tech block. This file test2.dat down here, that's the solution. The .dat file is the solution. It goes along with this .case file. Load ANSYS Fluent. Where is it? Fluent data loader. Fluent data loader. That's what you want. Not ANSYS, CFX, or results. You want Fluent data loader. You want to load casing data files. S2. And just turn on the contours. Use this magnifying glass to get a little better probably. Turn on these streamlines. Just say okay to this. And you can put a, if I press this icon, I can put it where I want. See that it's pretty well separated on the part. So I picked too big of an angle stack. We did that on purpose because we picked 10 degrees. That airfoil I think is probably better at 8 or 9. Of course, this is only a first order solution, but when I run a second order, the size of that separation region, but it's pretty heavily stalled. Yeah. And that's going to be unsteady. You know, it's not going to be that. You know, if you did an animation, you'll see this kind of wiggling around, moving around. Oscillating. And it oscillates because there are things are kind of reverberating around inside the tunnel. It doesn't make much shift slightly. And that will make the lift coefficient oscillate too. Anyway, we have a sane solution. That's one thing, a good thing to look at. Look at it early. Make sure you've got, especially if you have pressures that make sense. These pressures, these are relative to the atmospheric pressure that you're operating at. So the highest pressure here on the nose, or the top part here where the stagnation point is roughly 120 Pascal. So that should be roughly the dynamic pressure of the flow. So 1/2 rho v squared is 1/2. Rho is 1.2. V is 15. So what is that? 15 squared is 225. 225 times 1.2 is 250-ish. Divided by 2 is 120. So it's where it should be. Dynamic. So that's roughly the dynamic pressure of the flow. And then, so if you see numbers that are way out of this scale, then you got some problem. And it does happen. Fluent will allow things to keep running, even if you got this bizarre things developing in your flow solution. So you don't want to run it too long before taking a peek at it. Yes?
How did you import everything in this technology? Because I don't know whether they you said load case and data files.
Right.
And the case file is the file you used on Pointwise, right?
You have to save it within Fluent first. The .case file that you exported from Pointwise doesn't have everything set up in it, for one thing. And also it doesn't have the .dat file. Right? You need both.
Okay.
The .dat file contains the solution. The .case file contains the grid and the boundary conditions and all the settings for running the case. You need both of them to get this visualization. Anybody have any questions here? Went from Pointwise to Fluent to TechPlot. The major problem will be just having to run it long enough to see a clear history. If I run this long enough, what you'll see is this kind of an oscillation that's not going anywhere. It's clearly done. It's repeatable. You'll see repeatable oscillations, so that you'll know that there's no point in running it longer. It's not going anywhere. And once it gets to that point, you stop running it, and then you got to take an average lift and drag coefficient. That's the best you can do. In real life, it's not a steady lift and drag. It's, you know, it's measured and filtered by your wind tunnel equipment. You're going to have to filter it. I guess we can do that in a more fancy way. If we wanted to take the signal and filter it ourselves. You're welcome to do that. But that's what you're going to end up having to do. Is you're going to have to filter an unsteady lift and drag history from a virtual wind tunnel run, basically. You're going to run a virtual wind tunnel run. Any questions?